Welcome back, everybody. The aim today is to work on the exercise for this week. But I'm going to sneak in some 5-10 minutes just to wrap up this discussion which we had on Wednesday about the solution of differential equations. And then we're going to spend the rest of the time solving the exercises. And we can hang around till roughly 5 o'clock if you wish. If you have other obligations or appointments, I mean, free to do something else. So I just wanted to wrap up this discussion about differential solvers. And then we are going to, after these 10 minutes, I will just spend time on the solution of the exercises. And Shu Yu will take care of the people online. She's down here. And Abby comes around 4 o'clock as usual. So we should have enough time and enough people to help you. Okay, so the thing I wanted just to say a little bit about before we move on to solve exercises is about the solution of the differential equations. And also, I wanted to say something about the exercises which we have, some small hints and advice about that. So I will mainly be using this Jupyter notebook here and remind you a little bit of the kind of solutions which you can expect when you're solving also the exercises numerically. So what we have is what we call a second order differential equation. We have the acceleration first, a velocity dependent term, there is a position dependent term, and then there's a driving force. And the exercise number 4 deals essentially with studying this type of equations. Now, there are also, for those of you who may be interested, there are honors projects. And in one of the honors projects, you can actually replace this term, which goes like x of t, with a sine times an angle theta. And then you're going to simulate the mathematical pendulum. And that system is quite interesting because it also exhibits chaotic motion. But you can actually reuse everything which you have here, but then study a slightly different system. So I'm going to show you some examples a little bit later on how to use that one. So the thing which we went through on Wednesday during the last part was actually the solution of differential equations using these Runge-Kutta methods. So what we are providing is a kind of toolkit with different differential equation solvers in the same way as you would use ODINT in Python. Now, if you have a time-dependent force, and that's the case which we have in this exercise, then we will often have situations where energy is not conserved. So we're actually having a force which will depend on the velocity, on the position, and on time as well. And that means that in many of these applications, methods like Euler-Chroma, which we used, or the velocity Verlet, when we had energy conserving systems, they are not as good as the methods which belong to this class of Runge-Kutta methods. And this Runge-Kutta to fourth order is a method which actually has a mathematical truncation error, which goes like delta t to the power of 5. And it's a kind of industry standard. So if you're solving this type of equations of motion we have now, you will often see that many people use a Runge-Kutta to fourth order. And I'm providing you with the basic ingredients here so that you can actually play around with the same differential equation solvers. And the basic mathematics is actually given in you using one of the fundamental theorems of calculus and simply integrating up. And then what you end up with is this equation 3. And the whole family of these methods deals with how you approximate the integral. So if you start with the so-called midpoint rule, then you get something which is going to be Runge-Kutta to second order, or RK2. If you use Simpson's method, not the Simpson family, but Simpson's method, you're going to get RK4, and you will have a truncation error which goes like delta t to the power of 5. There are tons of variations of these methods, In addition to the Simpsons family, you also have the Adams family. There's another set of methods. And it's not the same as, obviously, the other Adams family. So let me just expose these methods here. And as we discussed on Wednesday, what you're doing now is to actually calculate this integral stepwise. And you use this formula here, and you need the function at y of I plus 1/2 step. And this is normally evaluated using Euler's method, because we don't know this value here. And with that, we typically defined on Wednesday a variable k1, which is actually the slope at the beginning point, multiplied with this step size. H is the step size instead of delta t, as I used on during Wednesday's lecture. And then you evaluate the final slope. So what you're doing then is actually you evaluate first one slope at the beginning, and then you reevaluate the slope at the midpoint, and then you use that value to make a prediction for the final point. And this is a method which has an error which goes like h to the power of 3, or delta t to the power of 3. And it's better than Euler-Kromer. It has the same quality as the velocity Valais, but then you can actually rewrite this in terms of the RK4 method, which uses Simpson's formula to calculate the integrals. And in that case, you actually calculate the slope at the midpoint twice, so you readjust it. And then you have the slope, which is then used to calculate the value at the final point. And you have the following formula, which is normally used to calculate the RK4 method. So these are widely used methods, and you'll be surprised by their simplicity. It's just you evaluating an integral with a given approximation. And these methods are the kind of standard methods. And people have actually written textbooks about these methods. You can find thick textbooks on only Runge-Kutta methods. So people dedicated their research life on studies of methods like these, their stabilities, different approximations, and so on and so on. Now, in our case, what we do now is that if you scroll down here, you will now see that we have tried to rewrite things in terms of methods. And I guess that some of you have already met object orientation and classes in Python. But what I'm doing here is just to give you a set of functions which you can use. And these functions then encode the different methods. So you will typically find the forward Euler, which we have met. You can define the force. So in our case, we have a force which depends on velocity, position, and time. And this is a typical signal that it's not going to be an energy conserving force, since we have this velocity dependent term, which gives a dissipation in energy term. And then what we can continue with, if we now just run through here, we can add the Euler-Kromer method. And you see here we set up the acceleration in terms of the force, where we now pass an equation for the force here, which is now a spring force, which you can change from situation to situation. So you can actually keep these methods as kind of black boxes and just change the forces. And we have the velocity Valais, which you have met before, which is widely used in like simulations of the solar system, molecular dynamics simulation. And here I've set up this RK2, but I've set it up in a not so, how to say, smart way, because I'm coding the derivatives for x and v. In many implementations, you will often see this just taking in an array with the unknown quantities x and v, and an array which contains the derivatives. But here I'm actually setting up the derivatives explicitly. Delta t times the velocity, and delta t times the force. Actually, this is the acceleration because I've divided by the mass. And then I set up this term k2, and then I do the final update here, as you saw from the formula in the text. And finally, I have this RK4 method where I do step-by-step velocity and position. So as I said, this is not the most compact and efficient way of setting it up, but I just put it up like this because we are going to deal with velocities and positions anyway. So it's more to visualize the kind of quantities which we're calculating the derivatives of. So these are, as I said, these are kind of really the industrial type of methods which are used to solve this type of equations. So what we end up with is a simple code where we actually have something like this. We set up delta t, a final time. We initialize time, velocity, and position, where we have the initial values, and then we set up the different parameters, and we can call the integrator which we want. So if you wish to compare these methods and see which one performs best, so the whole idea with a method like the RK4 is that the delta t error goes to the power of 5. So we can actually run calculations with a larger value of delta t, which means that if you simulate something over hundreds of years, this will be a preferred method, because then you can actually run it with a larger step size, because the truncation error you make goes like delta t to the power of 5. So that means that if you have 10 to the minus 2, your error scales like 10 to the minus 10 times something. And that means that you can run calculations with larger step sizes for longer times. If you were to use Euler's method, this would actually go wrong pretty soon. And then you would just make the step size smaller and smaller, which means that when you make it smaller and smaller, you can simulate for shorter times. So this is always this compromise. So when you're looking at the solar system, you can obviously use Euler-Kromer's method in the second midterm, but then you have to have a much smaller time step. If you use the velocity Vallée method, you can have a larger time step and simulate for longer times and get roughly the same type of error. So it's important to keep these things in mind, because the numerical methods represent approximations to the continuous equations which we have. Okay, so let's move on a little bit and just look at some examples. And this is something you will see in this exercise. As you see, I have an expression for the force now. And then if you run it, this is what you will get. And you see now I have an initial velocity. And after some time, the driving frequency of the force takes over. And it's going to oscillate back and forth between a minimum value and a maximum value, which is then defined by the parameters which I have here. So if you increase the amplitude of the force, this is going to give you a larger minimum maximum value. In this case, I put omega equal the driving frequency equal to the natural frequency of the system. And that means that this will actually swing a little bit. We will have actually larger values. If I make this smaller, then clearly I will get a smaller value here. So now you have a minimum which swings from minus 0.7 something to 0.7. So if I rerun it with those coefficients, you will see now that it swings between different values. And this is very much dictated by the value of this frequency here, the driving frequency, because now I made the driving frequency equal to 2 times the natural frequency. And this goes back to our discussion about the resonances which we had on Wednesday. Now, if you scroll down a little bit, there is another system, which is the classical pendulum or the mathematical pendulum. And normally you would solve this for small angles. And then the angle theta is sine theta is approximated with a theta. And then we have an equation which looks very much like the spring block which we had here. Again, here, you can actually reset the equations with a damping term and then the external applied force. Now you can have a sine. It doesn't matter whether you have cosine, sine, as long as you have a periodic force here. And then you redo the rescaling and you get then an equation here if you now change with a cosine. And then we have something which is pretty similar, except that now it's a nonlinear equation in the unknown parameter theta. So we have to deal with this sine theta term. This is an interesting system. By the way, the only thing you need to do is to change the force. Now you have a pendulum force. That's the only thing, and you can reuse these solvers again and again. But this system has some interesting results. And now you see something like this. Hey, what's happening here? This doesn't look reasonable. Actually, this system is a very interesting system because it leads to chaotic motion. So if you're interested in exploring these properties in an anonymous project, or you would like to explore that in one of the exercises later, please let me know. Because this we are not going to cover chaotic motion, but it's going to stabilize towards what's called a specific orbit, which is called an attractor. If I change these parameters, I will get a regular pendulum, which just swings back and forth as the spring force. So if I now change the parameters you see here for the different forces which are being applied, if I now change it back to, let's say I take this one, I think it was 1.0. If I do that, then it looks pretty regular, right? So I just changed now the only thing I changed was the ratio. Actually changed the damping factor, and that changes completely the behavior of the system. What I'm getting now is a initial condition which dominates in the beginning, and then the external driving force takes over and it swings back and forth according to that force. So the pendulum has a much, much richer behavior than this simple spring force, mainly due to the nonlinear term in sine theta. So if you're interested in exploring these things, please let me know. Now, one thing I wanted to say about the exercises, if we switch to that, if you look at this exercise 2, exercise 3, keep in mind that when you're making a plot, that you actually have a function of the absolute value. So you don't need to make a plot in terms of X, Y, and Z. The potential depends only on the relative distance and the absolute value of the relative distance. So you could now think of making a transformation to spherical coordinates and then simply make a plot in terms of the spherical coordinate radius. And there's no angle dependence. As you can see from the equation, there is no theta and phi angle dependence. So that means that in the exercise, just keep this in mind. And you need to tune a little bit the domains of the value r in order to have a plot which doesn't diverge, because your potential, when r is very small, it will be dominated by this 1 over r to the power of 12. So if you have 10 to the minus 2, you're going to get 10 to the 24th in the first term, times this parameter a. And then it's just going to explode for you. So you should narrow down the region. You can pick these variables, a, v0, and b as you want. You can put them to 1. In the plot which you see here, in the plot I've made here, you will see something like this. So there is a minimum, and it's not so different from types of potentials which you have seen before, which means that you can place yourself somewhere in this potential and get this kind of motion where you go oscillate back and forth around a minimum. If you give it an initial velocity and a specific potential energy, initial velocity 0, and then it would just oscillate back and forth between 2 points, as you saw in the midterm. Any questions so far? So you see this kind of exercise with the potentials, and from the potential we can say something about the type of motion which we can expect. So I'm going to stop the recording now, and then we just keep working on the exercises. Sure, you will follow people online, but if there are not so many, she will also rotate among us here. And again, feel free to ask questions, as many as you want. I'm going to stop the recording now.